Can you emote, please?
Maybe just go from start.
Start again?
Yeah, no, it was muted and the camera was.
Oh, okay. I'll start again. Okay. So, good afternoon, SCONA delegates, and my name is Patrick Warfield-McAlpine. I'm a PhD candidate under Kiao Imbathong, looking into virtual surgery and nasal physiology, also drug delivery. I was happy to collaborate on this paper, New Insights into Breathing Physiology and Transient Respiratory Nasal Simulation, with a large team of ENT surgeons and engineers. So I couldn't have done it without them. So the rationale for the study, so nasal airflow characteristics are heavily time dependent. However, the bulk of respiratory simulation studies are restricted to time independent simulations, so running steady state. This is most likely a result of the computational resource availability at the time of the study. However, computational availability has become a lot more accessible, and we have turbulence models that can actually reduce the computational requirements for simulation. Although a considerable amount of research is available exploring respiratory airflow computationally, the complete respiratory cycle and a high definition model from the nasal vestibule all the way to the trachea had yet to be completed, with idealized models often used or subcomponents to save time. To date, minimal studies focused on the air conditioning of the nasal trachea anatomy with the inclusion of the mucosal surfaces. As scale resolving models require significant mesh refinement to resolve sufficient turbulence, studies often limit their application to subcomponents of this respiratory anatomy. Apologies. This study aimed to employ a blending function to minimize total element requirements by applying a RAND solution at the near wall and an LES solution in the bulk fluid region. This isn't actually a turbulence model. It's known as the stress blended eddy simulation model, and it's just a blending function that combines the best attributes of the two models. So the methodology, so model construction and meshing. The model was received from an ENT collaborating surgeon through a segmentation of CT images using the 3D slicer software. To represent a volume of air being inhaled into the anatomy, a dome was positioned at the frontal section, you can see here, and the trachea was extended to ensure flow convergence. This was done using the ANSYS spaceplane software. The model was also wrapped using a fault-tolerant workflow in the ANSYS meshing software. This was to reduce leakage by covering the entire model and making it watertight. A polyhexcore mesh was selected to take advantage of the applied blended turbulence model. This mesh applies polyhedral cells at the boundary and hexahedral cells in the bulk fluid region associated with the RANS and LES requirements. To ensure the mesh adheres to the LES requirements, we followed the ANSYS scale resolving best practice guide and we consulted it and made sure that the low to delta ratio was greater than 5. Following simulation, the resolved spectrum was computed to ensure 80% turbulent kinetic energy was resolved only in the LES region. In the RANS region, we don't need to resolve turbulent kinetic energy. 6 boundary layers were applied to the near wall region, ensuring that a boundary Y plus of less than 1 was applied to adhere to the K omega SST model in that RANS section. So respiratory breathing cycle was applied as our boundary condition. This was following recommendations from a paper by Kamet et al. This cycle included a 4-second inhalation and exhalation phase at a breathing rate of 15 breaths per minute. The inhalation phase was considered parabolic, followed by following this empirical function that we've outlined here. And the exhalation phase followed the outline here, the equation here. So we applied 2 inhalation phases to remove startup effects and deleted the first phase. As you can see from As you can see from this image here, we have a comparison of the temperature, velocity, magnitude, and HBO fraction in those two phases. And you can see that we actually have startup effects on the first inhalation phase, whereas the second inhalation runs straight into exhalation. So we're getting a more accurate solution. We maintained a time step of 0.0025 seconds and a current number less than 1. So for the computational modeling, we used the stress blended eddy simulation model. So this applied the K omega SS or shear stress transport model on the near wall region using the conservation of mass momentum and an eddy simulation in the bulk fluid region with a wall adapting local eddy viscosity. The SBS model is outlined in this formula here. This is what switches between RANS and LES. If we have a 1 in this function, we can see that the LES cancels out and then we'll just have a RANS model. So this is an iterative process and actually moves through the geometry as the fluid flows. A submucous epithelial zone was estimated using an effective thermal resistance of 0.06 Kelvin per watt meter squared from Na et al. A water vapor fraction was applied to estimate humidity as a result of this mucosal surface using the following correlation. So exploring the peak velocity magnitude contours revealed some interesting insight into respiratory physiology, as the SBS model gave us high definition view of what was occurring within the anatomy. So during inhalation, the bulk fluid fills up the middle meters, as we can see in this section here. But negligible air enters the paranasal sinuses through the ostia. At the colana, 2 distinct streams of air, so that's the region at the back here, combined from the nasopharyngeal jet, propelling air toward the lower respiratory tract. This nasopharyngeal jet has not been seen in other papers before. This is a phenomena of the scale resolving turbulence model. So as the fluid passes through the anatomy, you can see rapid mixing in the inhalation phase, whereas it's quite smooth in the exhalation phase. This rapid mixing aids in moisture and heat transport. So it reaches more of an alveolar temperature faster as it goes through the inhalation. So I'm just going to go through. So we've made 2 animations to show what's actually occurring during the simulation. As you can see, it's in very high definition because it has this scale resolving model and the RANS on the outside to save computational power. You can really see that we have rapid mixing at this section here, the larynx, and a very smooth jet appearing at exhalation. So secondary flow structures during exhalation were identified. So the nasopharyngeal jet, which we coined, the pharyngeal jet and the laryngeal jet. You can see by the streamlines that we have rapid velocity increases as it passes through the anatomy at this pharynx section. And from the Q criterion, which shows the vortice magnitude, we can see these secondary structures forming at different sections in the anatomy. So plotting the nasal airway temperature during inhalation, exhalation is mostly isothermal, so we didn't provide that information. But we can see that temperature increases significantly through this nasal cavity, highlighting the importance of the nasal cavity and the turbulence in controlling temperature. We can see that the right nasal cavity is cooler than the left, which has been a common theme in these presentations, where they're not even. There's not asymmetrical fluid flow through both nasal cavities. And we can see this temperature imprint on the back of the nasal pharynx, which is actually a result of the turbulence, which hasn't been recognized in previous studies. So looking at the pharynx-larynx region during inhalation, we can see that alveolar temperature and humidity conditions are not achieved before the trachea. The trachea is not isothermal as previously believed. There's rapid mixing at the lower nasal pharynx and larynx entrance. This encourages heating and conditioning of that inhaled air. And the temperature is very clearly imprinted further down on this anatomy as well, as we can see the turbulent structures in these few sections. So having a look at the temperature and humidity, we can see that they're proportional to each other, as we would expect. we have a isothermal temperature and humidity during exhalation, but we do have changes in temperature and humidity during this inhalation zone, even as low as this C5 plane, which we can see in the red here, which indicates that we don't have alveolar conditions yet. So the new insights found from this study is that flow is predominantly laminar through the nasal section, but the proximity of the walls also provides compensation for the lower heat transfer of laminar mixing. At peak inhalation, the air does not reach alveolar conditions when it leaves the nasal cavity. It reaches them further down past the trachea. Enhanced turbulence mixing found in the larynx and trachea provides this further heating and conditioning of the inhaled air. That's through that mixing section. As we saw before, the exhalation is a very smooth jet. So during exhalation, the trachea produces a pharyngeal jet, which is not seen in computational models of the nasal cavity that end at this nasal pharynx, and also in models that use less fidelity algorithms. So we can see that the SBS provides a scalar resolving simulation. Results reveal this mixing. So if we were using a RANS model, we would average these velocity fluctuations, and we would miss these unique phenomena that were occurring during this study. So I have my references here that I use for this study, and if anyone has any questions, please feel free to ask.
Thank you, Patrick. So let's look at the questions. Okay, so the first question is, I'm interested in your model settings. How long did it take to model for the success?
How long was it completely to run the simulation? Yeah, so the simulation was run over a week. It had to be stopped and started at different points to adhere to the HPC requirements that we were using. So we don't have the full simulation time point. So we don't have the total time of simulation recorded, but we can check it. If you would like to email me, I can send that to you.
The second question is, what was the time step and the mesh size?
Okay, so the time step was mentioned before. It was 0.0025 seconds. That was to maintain a current Lurie number less than 1 for stability. The mesh size wasn't overly huge. I don't have the number off the top of my head, but it was much less than an LES simulation due to the very low Reynolds number that we're using through the anatomy and the fact that the LES is only being used in that bulk fluid region. Again, if you want to email me, I can send you the exact mesh specifications.